Hi, I'm Ryan, and today I'd like to look a little bit closer at a ubiquitous tool that is used to study decision-making in human and animal subjects. So decision-making experiments will often use a distilled down type of behavioral experiment that is pretty much akin to binary classification. And behavior is typically quantified using the psychometric function, which measures the probability of a particular action given the stimulus. So the psychometric function can serve as a sort of lens into the computations underlying decision-making, but what exactly is it showing us? I want to take a normative approach to this question, which will also end up telling us about how subjects ought to adapt their behavior to changes in the stimulus and reward distributions and how we'll see that manifested in the psychometric function. So in terms of the model, I'm going to assume that everything is independent across trials, so we're just focusing on inference and decision making. We're not concerned at all with learning. Okay, so we'll formalize the task like this. On each trial, we draw a category, a latent binary variable, and the stimulus from some joint distribution. And then we'll give a reward to the subjects stochastically based on the action that they take compared to the true latent category. Now, the decision maker in this case is a Bayesian agent who can only interact with the world through a noisy sensory and motor systems. It can't see the actual stimulus, so it can only see a noisy evoked neural response, which it uses to compute a posterior distribution over latent variables with the aid of an internal subjective world model. So it forms an internal binary choice using a policy function, which we allow to be stochastic. And a binary action is produced downstream where bit flip decision noise is added to the agent's choice. Now, in contrast to the agent, the psychometric function is computed from the standpoint of an experimenter who can see the true stimulus, it can see the action, but cannot see the agent's underlying choice, and it cannot see the neural response that it was based on. All right, so I won't have time to tell you about the results, but perhaps I can say some interesting points about them. In terms of how the agent should act, the optimal policy is to maximize the expected reward with respect to the internal world model. That turns out to be deterministic, so it forms a decision boundary in neural response space. It turns out that the reward distribution does not matter beyond the conditional means. So in fact, it doesn't even matter whether the reward is stochastic or deterministic. An agent only needs to keep track of just 4 numbers at most. It doesn't need to model the entire distribution. Similarly, the decision noise doesn't need to matter. There's nothing that an agent can do to mitigate the bit flips, so it doesn't need to model them. And discriminative and generative models turn out to perform identically in this context, so the agent could use either one. In terms of the psychometric function, it is a stochastic account of behavior due to the experimenter's ignorance about the internal state of the agent. And its shape is predominantly determined by the sensory noise distribution. For example, that characteristic sigmoidal shape that we often see in the psychometric can reflect the CDF of the sensory noise projected onto a low-dimensional neural manifold. And in terms of decision noise, the only real effect on the psychometric function is to vertically shift and scale it by a constant. So the model will also tell us how subjects ought to change their behavior when we do things like switch up the stimulus distribution, the category distribution, the reward distribution, and how we'll see that reflected in the psychometric. We can compare that to experimental data collected by the Akrami lab in human rat and mouse subjects. Athena is going to describe these experiments tomorrow, but what we generally see, at least in terms of the psychometric function, is that all of these subjects adapt their behavior to changes in the stimulus distribution similar to the normative model. But of course, this doesn't account for learning, which Athena will tell you about tomorrow. So if you'd like to hear more, I'd love to chat during the poster session. Thank you so much.